So the question, how do we answer which test? Before you do that, you really need to think, what do I want right at the end of whatever the program is that I'm putting together? What's the purpose? Is it for design? Is it for geomet modeling? What type of circuit? There's obviously no point in choosing an Ore characterization test, for example, for crushers, if the circuit you're interested in is a ball mill circuit. I know that might sound obvious, but in my experience, I have quite often come across cases where people have really seriously not thought through that particular process. What type of circuit? What are you expecting to get at the end of your program? Is it just simply a throughput prediction, or do you want to do JK simulations? Again, I've had cases where people come to me, say with an SPI test, and ask me, can I do a JK simulation? The answer is no. They simply have not thought through the program from the beginning. Last but not least, an Ore characterization test is absolutely useless unless it is partnered with some form of an equation or a simulation model that's going to predict what you want, whether it's specific energy and throughput. So you have to look at both those things together to answer the question of which Ore characterization test should I use. So you've been through that process. Now, how do you go about choosing the right test? As I said before, the laboratory test and the equations that use the results are intimately linked. So you really have to be very clear in your own mind about which of those two partners you're going to choose. Your decisions should be, they're not always, but they should be based on statistical aspects. How precise is the test that you're proposing? How accurate are the equations that are going to be used that are inputted from those tests? To answer that, you need reliable information from quality control, from laboratory tests, or good old observed versus predicted numbers. So what tests are available? And I've put up here my top 6, and that's based on the numbers of tests that have been done, how popular they are over the years. Clearly, bonds tests have been around now for the best part of 60 years. They still are some of the most popular characterization tests. Crushing, rod mill, ball milling. The SPI test, their website I don't think has been updated that recently, but a few years ago they had done something like 25,000 tests, so clearly a popular test. JK drop weight test and the SMC test. Each of these tests are used for different purposes. The top 4 can only be used to obtain kilowatt hour per tonne numbers. JK drop weight test has been designed specifically for simulation purposes, and the SMC test has been designed for both purposes, both for developing kilowatt hours per tonne figures as well as simulation. Each of the tests needs different amounts of masses. Bond crushing, as you can see, is up to 40 kilograms, whereas the SPI is down to 12. So the amount of sample that you have available is also clearly very important. So how good are they? How accurate are they? Matt is going to talk in a couple of presentations' time about statistics associated with precision, reproducibility, repeatability. These precision data that I've shown here have come from a number of published sources. Those for the bond test, 2 guys, Angove and Dunn, about 20 years ago, did a really, really good investigation of the precisions of those tests. And I would strongly recommend, if you're interested in this area, to read their paper. The crushing work index test turned out to be probably one of the poorest of all. And to be honest with you, I don't know why anybody anymore would want to do a bond crushing work index test. With the sort of precision, and precision here we're looking at coefficient of variation, standard deviation over the mean. The 95% confidence interval for a bond crushing work index test is plus or minus 70%. So that's the band that the number could lie in. Well, that's not much better than a random number generator. So beware of doing a test like that because it has extremely poor precision. The rod-mill work index comes next, obviously a lot better. One of the problems with the Bond rod-mill work index is that different laboratories have different designs of rod-mill. Bond specifically dictated the design of the Bond rod-mill. And if you want to get the right result, you have to follow Bond's dictates. Some laboratories, for example, don't use wave liners in their laboratory mill. And Bond specifically said your mill should have wave liners. So you can see here the confidence interval is about plus or minus 25%. Bond, much better, the Bond ball mill work index test. Matt's going to talk about some of these results because we've been studying, or JK Tech has been studying them. You can see here coefficient of variation is about 8%, so the confidence interval there is plus or minus 14. SBI test, I've never ever seen any published results. Whether SGS has some internal results, I don't know, as SGS owns the SBI test, but I've never seen any published work done on the precision of that test. I would imagine it should be reasonably good. It's a tumbling mill test. I'd be very surprised if it's not as good, at least as the Bond ball mill work index test. JK drop weight and SMC tests have very similar precisions. These two tests, there are a huge amount of data that have been generated from a series of programs that JK Tech started back in 2008. Every single laboratory in the world that has a drop weight tester gets involved in this test. So it's the most detailed amount of statistical information of any of the tests that are currently available. And Matt's going to talk about the background behind that and, as I said earlier, issues associated with precision, reproducibility, and the like. All right, I'm going to concentrate on the drop weight test and the SMC test. Drop weight tester, first of all, is the device that's used to do both the drop weight test and the SMC test. This is me, believe it or not, about just over 30 years ago. This is the very first JK drop weight tester that we ever built. This was the prototype. I was running the research program at the JK MRC in the 1990s. And one of the guys that worked in the lab came to me one day and said, "Steve, I've got this idea for a drop weight machine. What do you think?" So I said, "Yeah, let's build it." And the reason I was very keen to have that built is at the time we were very interested with the SAG mills at being able to break big rocks. And at the time, the machines that we had in the laboratory to break and study rocks, we could probably only get up to about, say, 1 inch. And as you know from SAG mill feeds, those rocks are very much bigger. So the original intention of this device was to break bigger rocks. So what constitutes a drop weight test? 5 different particle sizes are broken in a drop weight test at 3 different specific energies. Size fractions vary in the range -63 plus 13.2, so 15 data points are generated from that test. Typically you need PQ core, and for those of you who don't know about cores, that's 85mm diameter core. The kilowatt hours per ton, the specific energy that is used in that test, comes from the potential energy of that drop weight, obviously divided by the mass of the particle. And that kilowatt hours per ton is related to the product size distribution using this T10 parameter. Now, I'm not going to go over the T10 parameter in any great detail. If I did, we'd probably need another day for this masterclass. It is a concept that some people find difficult. As a student, I found it difficult. If you find it difficult, therefore, don't worry about it. Certainly, the JK run training programs for those people who do JK SimMet, and they do spend quite some time looking at the whole T10 concept. I will be talking a little bit about it, but obviously in limited terms. The output of those tests are A and B parameter, and that's used for AG and SAG mill modelling. Something called the SCSE, and I'm going to talk a little bit about that because that's a fairly recent innovation. There's an appearance function, which is a modelling term, and there's an energy size matrix for crusher modelling. And last but not least, actually very important attribute, I'm surprised so many metallurgists ignore it, specific gravity. It is very, very important. This is I wouldn't say typical because I've contrived this to some extent, but here are some drop weight test raw data. There's the 15 data points. Here's the T10. The T10 you can think of is an index of fineness. The bigger T10 is, the more fines there is from a breakage event. And on the x-axis here is how much energy you put in. So clearly those points follow a pattern that the more energy you put in, the finer the product is. And so the T10 goes up. JK Tech take those data and they fit a single line. The best fit statistically they can, that's that dotted line. And that dotted line follows that equation, which was developed in the late 1980s at the JK Centre. So there's the T10, there's the specific energy, and the two parameters that we're interested in is A and B. A is that line there, and that's the line ultimately that our fit finally joins. It's the asymptote to that line. B is related to the gradient of that curve. A times B, which you'll often see, is the gradient at zero energy. If you're any good at differentiation, if you differentiate that equation with respect to energy, put energy equal to zero, you'll find that that is what A times B is. SCSE. I think it was about 3 years ago we introduced this, and you'll see it in all of JK Tech's standard reports. It comes from both drop weight tests and SMC tests. The reason for it is that A and B were originally meant for simulation, and they are really good parameters to use for simulation. As the years went by, this term A times B took on a life of its own. Everybody was quoting A times B. It is a valuable number which indicates hardness, but it is an indicator only. There's no hard numbers associated with it from an engineering perspective. It's non-linear, and that's the biggest problem. For example, if we look here, let's say you had an A times B of your rock of 10%, and you had another rock which had an A times B which was 10% different. It doesn't mean that the rock is 10% difference in hardness. If you were to run those numbers through JK SimMet, which is what they're meant for, that 10% change equates to a 4.6% change in specific energy. It's almost half. However, if we started with an A times B of 300 and went through the same process, a 10% difference only relates to a 1.8% difference in specific energy. So serious non-linear changes. So what we decided to do is to develop a standard test. Let me go back. We're not a standard test, a standard output from the drop weight tester, which was linear rather than being non-linear. And that basically was looking at the output from a simulator. And there's the simulator circuit. It's a JK SimMet circuit. It is the same circuit we use every single time. Every time an A times B is generated, effectively that number is run through that SABC circuit, and the specific energy that it generates is quoted in the JK drop weight test report that clients receive. They are the conditions of the simulator. And if you wanted to, and you had a JK simulator, and you were given an A and a B, you could generate the same SCSE values that we generate in that report. But the SCSE change is linear, not with A times B non-linear. Let's go on to the SMC test. That was developed by me back in 2003, and it was specifically developed so that you could use small amounts of drill core. Everybody wanted to do drop weight tests, but often were put off with drilling programs for the need to have large amounts of PQ core. The SMC test can use HQ, NQ, or even BQ, 65mm, 50mm, 25mm core. You can use half or quartered core, and you can use as little as 2 kilograms if you really have to. It uses the drop weight tester, just like a drop weight test. It has a range of outputs, however. There are power-based outputs, and we're going to talk later about power-based equations. They are the drop weight index, MIA, MIC, MIH, and then just like the drop weight test, A and B parameters for simulation modelling, plus the SCSE. You can get the appearance function for the crusher model, as well as the energy size matrix for the crusher model and the specific gravity. The test can either use the core, which is cut up using a diamond saw, and that uses the minimum amount of material. It's very economic in material. Or you can crush that core and use crush rock. You need a little bit more sample than that. 3 different size fractions you can use, and that will be dictated by what, as the mining company, you have available, and also the amount of sample. So as a client, if you want an SMC test being done, then you need to make sure that if you want it done on that particle size, you need to provide enough information, enough rock and a sufficiently large drill core for the laboratory to be able to do that test. So what's the procedure? At the laboratory, so if, let's say now we're at SGS, the laboratory measures the SG, it will cut or crush the core that's come from the client into pieces, selects those pieces and breaks in the drop weight test at 100 particles. 5 different energy levels are used, so it generates 5 data points, not 15 like the drop weight test's done. The products are sized and the raw data then goes to JKDWT. To compare the data, if that is a drop weight test, and we can see there's the 15 data points, SMC test only uses 1 size fraction, but it looks at that size fraction in a little bit more detail. It has 5 data points associated with it. So that's the raw data. So the raw data has now gone to JKDWT. That information goes to Matt and his team. He does a certain amount of initial data quality checking, and that information then is passed on to SMC testing. SMC testing does further quality checks, and the raw data is then subject to a number of algorithms, and it generates those power-based parameters, the DWI, MIA, MIC, and MIH. Raw A and B data are fitted to that raw data, and where necessary, those values are scaled. We used to call it calibration. Calibration is the wrong word. It's scaling, and I'll explain why in a minute. The other parameters like the TA and the crusher appearance function are also generated. That report goes back to JKDWT. JKDWT does final checks, passes that on to the laboratory, and the laboratory goes on to the client. So that's the whole process. So what's scaling and why is it necessary? Well, once again, let's look at our drop weight test raw data. There's our 15 data points. And as I said before, if it was a drop weight test, one line would be drawn through those points. Here's an example of a drop weight test that generates an A times B of 45. Now, although one line is drawn through this, research back in 1990 found that actually there's 5 lines there. Every particle size actually has its own A times B. So, for example, although the A times B on average is 45, this relatively small particle here, 14.5, actually has an A times B of 35. This big particle has an A times B of 65. If we plot all those A times B's against particle size, we end up with this. Here's our 5 different particle sizes, and here's the A times B. And there is a typical relationship between A times B and particle size. The drop weight test, however, generates the value of 45, which is on average the same value that approximately a 28mm particle will give. So on average, A times B from a drop weight test is similar to the A times B of a 28mm particle. So if we have a look at our SMC test, which is done on a 28mm particle, it should be no surprise then that the raw A times B is 45. It's very, very similar to what the drop weight test will give. So if we look at that result, the SMC test result, there it is, that red dot. There's the particle size. It was done on a 28mm particle. There's the A times B value there. If we had at the same time the drop weight test information, that curve there, we could see it's been done on a 28mm particle. That's what the drop weight test would have given us. Therefore, there's no need to scale. That's the result, and that's the result that would get quoted. Let's say, however, you aren't able to use a 20mm particle. The client has sent you material, the lab this is, you can only get 20mm particles out of it. So here's our SMC test raw results from a 20mm particle. SMC test has fitted the raw A times B. It's 40. Let's go back to our curve. There's 40 being plotted on our curve. It's done with a 20mm particle. If we knew the shape of that scaling curve, then we would use that shape to slide that particle size up to the equivalent of 28mm. There's the shift in size. And there is the scaling factor, the scaling that we've needed to do to adjust that 40 A times B to 45. And there we've got the right answer. But we need to know the shape of that curve to be able to do that scaling if we have a 20mm particle. If we had a 14mm particle, we'd have to scale even more, but we'd still get back to the correct answer. So, to summarise, if the SMC test is done on a 28mm particle, no scaling is required. Therefore, if you are a mine or a lab that has the choice, and you can choose any particle size you want to do an SMC test, the preference is try and do it on a 28mm particle, because then the whole scaling issue disappears. We don't need to worry about it. If you have to use 20 or 40mm particles, it's not a problem, but you've now got to think about scaling. And the question that first comes to mind is, how do I get the shape of that curve that I showed you for you to be able to do that scaling? Well, of course, you can either do a JK drop weight test, or the other choice is to use the SMC testing database. Before I go on a little bit more to tell you about the database, just remember, scaling only applies to the A and B values. It does not apply to all the other parameters from the SMC test. DWI, MIA, MIC, MIH, they are inherently scaled. You don't need to consider scaling at all. So, you've not You've decided, or your client's decided, we're not going to do a drop weight test on that ore body to get the scaling curve. We're going to use the SMC Test database for that. Where does that database come from? Well, it comes from looking at well over 2,000 historic JK drop weight tests, looking at every single one of those scaling curves. What we found is that most of the time that curve is exactly the same. It doesn't matter where you are and what the deposit is. And that shape there on that dotted line is the average of that database. That's the database mean. Those green lines are the 95% confidence limits looking at that database. That's how much 95% of those curves varied in that database. So let's quantify now what could potentially happen if you decide, I'm going to use the database. I'm not going to use a drop weight test for my scaling factor. Just how badly can that go wrong? In other words, let's say in your deposit, if you knew that deposit and you were able to do a drop weight test, the scaling factor, rather than being on that red line, is out on that green line. You didn't know that, and you then processed your data. How much of an error would that introduce? Well, let's look at a 20 millimeter particle. And what I'm showing here is from your sample. That's the true A times B of the sample. And this is the error associated with that mistake that you've made. You've chosen the database for scaling, whereas the true scaling factor is way out on the 95% confidence interval. So here you can see how much percentage-wise that mistake will be. And at most, it's just over 3%. So it's not huge. And that only occurs when the rock is really hard. If you're down at this end when the rock is really soft, it's only about 1%. If you choose a 14 millimeter particle, the error is slightly larger. You can see we're up to 6% is the error associated with it for a very hard rock. And down here, you can see it's only about 2%. And just to remind you again, if you use a 28 millimeter particle, there is no error. There's no error associated with using either one of those two. It makes no difference.